All right, welcome everyone. This is Nonlinear Dynamics and Chaos 1. My name is George Haller, the instructor. And before I start, I will say that I really appreciate if people make themselves visible. It makes it more personal for me, because otherwise I just end up talking for an hour and a half to myself. And it makes a whole lot of difference. I realize if you sometimes need to block it off because you need to do something. I do the same in meetings, but if you think that you don't mind doing it, and I certainly appreciate it. Similarly, just for the logistics, I know that people tend to use the chat a lot, and maybe I realize that some people are more comfortable with that, and the more interaction, the better. But again, feel free to ask a question as you would in a classroom. So, just say, excuse me, question or something, and I'm happy to stop. There's not a whole lot of people. We're not talking about hundreds of people. Right now, there's 42 online. So just like in a classroom situation, but the chat is also available. And for some reason, you want to wait with your question of time, that's fine, okay? The title of the class, Nonlinear Dynamics and Chaos 1, I'll explain that because that's what the class is all about. Let me say just a few words about this cover illustration. I just picked that. I find some of the atmospheric and oceanographic images fascinating and very relevant for nonlinear dynamical systems, because nature is full of nonlinear complex behavior. And the reason why I picked this one, this actually shows an enhanced image from NASA of the cloud cover of Jupiter. This is the atmosphere of Jupiter, if I remember correctly, from a recent mission. It really kind of gives you an illustration of the complexity of a dynamical system. This is a dynamical system. This is not a static image. This is the atmosphere. And what you see here is basically enhanced images of gas distribution, various chemical distributions. They are constantly in motion. It is a dynamical system, and it tells you how many things can happen concurrently in the same system that are really different from each other. And that's, in one word, maybe that's one thing that distinguishes nonlinear systems from linear systems, that they have alternative, sustainable, competing behaviors, whereas a linear system does in the large exactly what it does in the small, right? It scales up. A nonlinear system is very different from that. And a nonlinear system is pretty much reality. Every linear is an approximation, and the reality is nonlinear, right? So this course is all about bringing that out and not making the assumption that the system is linear, which you need to realize is a modeling assumption that we often use. But why would anything be exactly linear? So the world is nonlinear, and this just gives you an idea of the complexity of that nonlinearity to the extent it can be complex. I just need to advance this. The course will not be PowerPoint. These are just the introductory slides, and you will find copies of these in Moodle, which I've already deposited. So I'm going to be writing on a tablet. It also enables me to show pictures, maybe even play movies. So this is only the first few things that I just wanted to show to make sure I'm not forgetting anything. There we go. So the course outline is the first thing I wanted to mention, and then a little bit about the logistics. I just need to position this bar a bit better so that I can see the title that I want to talk about. Okay, so I just want to flash things that you will hear about in more detail. I'm going to talk about basic facts related to nonlinear dynamical systems that I want to clear up: existence, uniqueness, dependence on initial data. This will be not a strict theorem definition format, which I'm trying to avoid as much as I can in this class, but I want to bring in hard facts that you can use. The idea is I want to bring in mathematical facts about nonlinear systems, not just for the sake of doing math, but rather these are the fundamentals that I find very important in evaluating simulations, results, planning research ahead. So these are fundamentals that should infer your view inform your view on nonlinear systems. What are the possibilities that can happen? What are the things that we know for sure? And what are the things that might be system dependent, or what are the things that we don't know for sure? So that's just to clear things up to get started. Then the whole view of this course is the modern view of dynamical systems, which is geometric in nature. So rather than plotting variables in time and wondering where they are going or where they've been coming from, we adopt the view of the phase space, which is basically the space of dynamic variables in which the evolution takes place. And as you will see, that's a very geometric notion, because you can picture the evolution of the system not as something oscillating, not as something jumping on a screen, but rather actually a trajectory moving forward. So one particular point in the appropriate phase space determines the location of any system. And that can be a system that has only 2 dimensions, 1 dimension, or maybe a million dimensions. In the appropriate phase space, and this is a major simplification, the current state of the system is just 1 point. And the evolution of that system will be then basically a trajectory. This is the geometric view. And then we try to build up that view from the basics. So we start near equilibria in the phase space, look at their properties, and then basically we extend them to more global considerations, but we have to start somewhere. So that's why we start with near equilibrium dynamics. Okay. This being recorded. Okay, got it. The next thing will be bifurcations of equilibria, which means what happens when you change parameters in the system. Why would you change parameters? Why would you change the properties of the system? Well, for one thing, you never quite know a system exactly. I mean, the things we work with in nature and science and technology, they are models. And as such, they have uncertainties, and they also have sometimes design parameters that so in a case of uncertainties, you just don't know what a certain parameter is. In the case of design, you actually realize that you have some freedom in changing those parameters, and you might want to change them in a way to influence the behavior of the system. So either way, there will be clearly some dependence on the variations in parameters. And what may happen is that what used to be an equilibrium all of a sudden is not an equilibrium, but maybe 2, maybe more, and maybe even disappear. So that's the first real dramatic thing that can happen in the life of a dynamical system in the small, that an equilibrium changes. So we're going to talk about techniques for understanding that. These changes can have really dramatic consequences in the locally. Obviously, we would like to extend our knowledge from equilibria to more global considerations or near equilibria. But the thing is that that's still an unsolved question, probably will remain unsolved forever to some extent, because nonlinear systems are not explicitly solvable in general. But there are some cases in which you can get a fairly complete knowledge of the global dynamics, and those will be nonlinear dynamical systems on the plane. So you basically restrict to 2-dimensional systems, then we can have a fairly complete global understanding. So I'm going to get into that. Then I will add a specific treatment of time-dependent dynamical systems. These are dynamical systems whose evolution rule, we'll learn about that soon, changes in time. So it doesn't remain the same. They keep changing their behavior. These are even more complicated than the ones that we call autonomous, which do not change their evolution rule. So this is a big subject, but we're going to talk about just the basics of that at that point. And then, if depending on how far I get with the material, I get started on chaotic dynamics, which will be continued in part 2 of this course. Although, as I noticed, some of you have already taken part 2 and not taking part 1. So for you, now you'll see the motivation for that. Chaotic dynamics is probably the most complicated form of dynamics that can occur in simple and still deterministic dynamical systems. So these are not stochastic, random dynamical systems, but deterministic ones, and yet can produce incredibly complicated behavior. And these are the things, some of the technical terms that you might not understand at this point, but hey, that's what we're here to learn. I recommend some books. My all-time favorite has been Guggenheimer and Holmes, Nonlinear Oscillations, Dynamical Systems, and Bifurcations of Vector Fields. I think it's an incredibly insightful book. And it was written in the 80s. It has a few revised editions, but I just think that it has everything, right? There are also textbook, undergraduate textbook level books, and I'm sure they're always the most recent ones, but I personally find this the most insightful book of all, and it's not that thick. There's incredibly thick books with multiple volumes. There's also other books with incredibly detailed theorems. The genre of the subject is that some authors and some practitioners of the field are fully focused on the mathematics. Others are fully focused on applications. And what I find is that this book really hits the right balance, proper motivation and also applications. Perhaps because actually one of the authors is a mathematician, John Guggenheimer by training, and Philip Holmes was an engineer by training, although he became pretty mathematical. So that sort of diversity of viewpoints is there. I really like the book by Ferdinand Verhulst as well. He is a mathematician, but he's a master of simple exposition and writing, and he's interested in applications. So his book is non-linear differential equations and dynamical systems, very readable. A bit more on the classical side. Vladimir Arnold's classic is ordinary differential equations, more about the basics, less about applications, but a beautiful example of the geometric view for the basics. And Steve Strogatzy's book in nonlinear dynamics and chaos is a pretty popular book, and it's a very sort of popular exposition. He's a master, Steve Strogatzy, of popular exposition. He's also done, since this book, has done a lot in terms of promoting mathematics in general, not just dynamical systems. So these would, again, you find these slides again, so I'm not going to spend too much time on that. Now, the logistics of the class. So some of how the class is going to proceed first. So first of all, the course information, everything that I cover here will be on Moodle, including links to the recorded videos. And here's the link, but you can just go there directly from my studies or whatever your interface is. Different from mine. Mine is eDots. Prerequisites. Not that I checked this, but I mean you will find, if you don't have the proper analysis background and some basic course in differential equations, then this course might be hard, because I'm not going to get into all details. So what do I count on? I count on you knowing multivariable calculus reliably, linear algebra reliably, and you have seen differential equations before. Having said that, I will try to review everything on the fly, maybe in a few words. But I think that if you don't have this background, which I declare for this course in the course catalog, then you may have a hard time following the course. So that this needs to be there. Maybe you can just tag along for a while and see what I mean by this background. But pretty much it's multivariable calculus, Taylor expansions, differentiation, power series, some elementary solution of elementary differential equations. Okay. The exam, the most important thing. So it's a 2-hour exam in English. We've already fixed the date. It's on Moodle. It's essentially the last week of classes, because the last week this year really goes way up to Christmas. And I didn't want to wait till the very end and keep people here. I'm sure everybody has vacation plans. And instead of having it on the last day, which would be the 23rd or something, I decided to have it on Monday. Okay, which means that I don't want to misspeak, but I believe that it's going to be on Monday, and that means that we would still have 2 classes formally, which I still hold for information purposes, but those will obviously not be, the material covered there will not be featured on the exam. But again, I didn't display it here, sorry, but you can really find it on the Moodle page. There will be problem sets. Now, ever since we moved to this Zoom format, which I'm now following this semester again, because I did a vote, an opinion poll, and interestingly, when I put out the poll, within the first, I don't want to be kidding, but I think I'm not exaggerating, within the first 4 or 5 minutes, I got 8 votes for in class, and I got 1 vote for this, what we're doing now. And I said, okay, so that's what we're thinking, professors, that the students just overwhelmingly appreciate the in class over the Zoom, right? And I said, okay, and then I let it for a while. And the next time I come back, then it has completely changed by that time, right? And I really honestly tell you the truth that by the end, it's that twice as many people, nearly twice as many people voted for the Zoom format than for the in-class format. Now, as far as my format, I absolutely prefer the in-class format. I feel much better about it. There's much more feedback. I can connect with the audience. I like moving around, writing on the blackboard. I don't like this, but I also don't like talking to 3 people in the classroom. And given all the current COVID rules, I would have to record this lecture anyway, right? So that's why that's why I popped the question. All right, but apparently people don't mind. So that was a long-winded introduction to the problem sets. Well, how is that related to the problem sets? We used to require before this online format that people actually turn in problem sets for a grade. We don't do that anymore. What we do instead is that there will be problem sets given out. You have time to look at them, and then you will have these problem sessions which you can attend online if you want to. It's strongly encouraged, where Dr. Shobi Jain, who's also here online, and we'll say a few words when we get to that point, will discuss the solutions of these problem sets. Okay, and after he discussed that, he will actually post the solutions. Okay. I mean, if you really want, you can get to those solutions, I'm sure, from last year, but it's more just to help you psychologically. We're not giving out the solutions. Maybe you think about the problems a little bit, then you hear the solutions. And if something is still unclear, then you can look at the solutions, right? And you're strongly encouraged to solve these problems and participate, but they're not mandatory. Why would you then do it? You would do it because we're not giving out homeworks, and this is your only opportunity to practice for the exam. On the exam, you have to solve problems related to this. And if you just come armed with some theoretical knowledge and you have never solved any problems, or you've just kind of been sitting through the problem sessions and like they said, yeah, I could do that. Yeah, that makes sense. That's not going to be enough. So you have to have some experience in this. And I'm sure you've seen that with other subjects that are mathematical, that an agreement on your part does not constitute knowledge of the material. So some practice is required. Having said that, this is not mandatory. So don't tell me that we're requiring too much for the 4 credit. You don't have to attend it, right? This is optional. It's supposed to help you, right? Before you suggest that why would you complain? I'm just saying that each year we get some people complaining that we're asking for too much. You don't have to do it. It's supposed to help you. You don't want to take it because you can prepare on your own, fine. So the solutions will be posted after the problem sessions. The lectures, online lectures, since you're here, so those of you who are here, you correctly guessed that the first lecture is always in Tuesday in this time slot. The next one is on Wednesday. I'd like to point out that we do keep for now the reservation for the classroom for those of you who might be on campus, right? And because you're attending some physical lectures and you would like a quiet place where you can sit down and just listen to this class online. So these will be held, these reservations for now. And this is since you're here, you know that this is the Zoom ID for the class. So the online problem sessions will be on Mondays from, well, roughly from 5:15 p.m. To 6. That's the 45-minute problem session, I think, that we agreed on. And Dr. Shobi Jain will be in charge of this. He's a senior member of my group and is very familiar with the material and has done it before. And he's online, so I'm happy to introduce him and ask him to say a few words, just a few words about what he thinks is important for the problem session.
Thanks a lot. Hi, everyone. So my name is Shobit Jain, and I'm a postdoc here in the chair in nonlinear dynamics. So the idea that we have for the problem session, as Professor Haller already mentioned, is that we would be looking at some very exciting problems, and you would be seeing problem sets, which would be posted on the Moodle, on the link that you're seeing here on the screen. And on the same page, I would also be posting which problems we would be focusing on in the upcoming problem session. Now, it's very important that you try to give it your best shot to try and solve these problems. And then, of course, if there are doubts or questions and you want to see a solution, then we would be trying to walk through the solutions during the problems as something very informal. You could always try and propose an alternate solution, discuss the solutions that you may have, or any doubts that you may have. So I look forward to seeing many of you in the problem sessions, which would be held weekly. Yeah.
Excellent. Thanks a lot. Next item to discuss is online office hours, which we will have every week, starting this week on Friday. These are designed to be an hour and a half, but I mean, if we need to go overtime a little bit, a few minutes, that doesn't matter. The idea there is that these would help you with questions related to the problem sets. Also, if you have questions about the lectures, you can bring those to these office hours. The person in charge of the office hours will be Balin Kossash, who's also a member of my group, and he's also very familiar with he works in this area, nonlinear dynamics. And I also asked him to say a few words as to what he finds important to be mentioned about the office hours.
Thank you. I also welcome everyone. It's nice to see you. I'm Balint, and the idea would be that if you need additional help with these problem sessions or need help preparing for the exams, you can come to me with questions. And I'll be available every week on Friday afternoons. But if something comes up during the week, outside of lectures or the problem sessions, you can also reach me by email. I think that's on the Moodle page somewhere, or you can find it on our group page. And I'll be happy to help with that way also. And I look forward to seeing all of you, and good luck with the semester.
Great, thanks a lot. In the meantime, I'm displaying the common Zoom link. Both of these activities will be online, and they have the same Zoom meeting number. Again, this is all in the PowerPoint that you find on Moodle. So that was pretty much, well, the last thing I wanted to say, how do I go back? Just in this round, of course, if you have questions, you don't necessarily have to wait till the office hours. If you have some burning question that you would like to ask during the lecture, I'm more than happy to stop and clarify. No problem with that. And also I can stay on. In some cases I have to run, but pretty much as a rule, I'm happy to stay on after the lectures and answer questions while these questions are still fresh in your mind. So you can count on that as well. I always stay on. Sometimes I ended up staying on 15, 20 minutes if there were questions, okay? So that's also absolutely okay. Any questions regarding what I have covered so far? Because this is where the logistic ends. If not, then I would just like to move on just to some basic motivation for the course. I like to show this movie usually, when I get this out of the way, as a motivation. One of the mottos of this class and one of the mottos of modern dynamical systems is that complex systems can show simple behavior, okay? And this will be one example of that I want to show, but I will also add that this doesn't happen all that often. In this video, a complex system will show simple behavior after 605 trials of the same process. You will see in a second. This was a commercial for a Honda car, and I think this is now several years old. And at the time, just by way of introduction, the word has it that this was a commercial to sell the car in North America. And when it was shown to the upper management of Honda for final approval, they said that, wow, it's really amazing how far computer animation has come over the years, because this is clearly not reality, but this was just manipulated by a computer. And they were shocked to find out that no, this was an actual experimental choreographed process, physical process, without any computer tricks and animation. But it took 605 trials to get it right. And chances are very high that for the next time, had they tried it, it wouldn't have worked again, okay? Because the system that you were about to see is incredibly complex, and the intended behavior is highly atypical, required a lot of tuning, and almost just happened as happenstance for a second. So this was the commercial. Hopefully you will hear the video as well. It's called the cog because it starts, the cog wheel starts the whole thing. No computer animation in this, just purely a shot of what happened. I think it almost hurts to watch after a while. For me, every time I watch it, almost hurts.
Isn't it nice when things just work?
So beautiful. Yeah, and I'm not getting any cut from Honda. I don't think you can buy this Accord anymore, but it's pretty amazing. And it just really shows that this incredibly high degree of freedom problem, too many to count, given that it took them 605 trials and constant tuning and tuning to get the required outcome, it's highly sensitive with respect to initial conditions and changing in parameters. And that's what a typical dynamical system is. So complex systems showing simple behavior is quite rare, even though it can happen. The other paradigm, or the other, almost the opposite, and I have to actually, I don't want to play this again, sorry, I just need to get to the following slides, is that the opposite, that simple dynamical systems may show very complex behavior. And they may show that right away without any tuning, okay? And that was perhaps the even more surprising part. And this was inspiring to the development of modern dynamical systems theory, because people didn't realize this. People prior to this realization, which probably comes from the 1960s or so, 70s-ish, people believed that if they saw some complicated phenomenon, then it had to be an underlying complicated dynamical system producing that. And when they saw something unexplained, they said, okay, my simple model, there's no way that with 2 or 3 equations I can generate that complexity. I probably have to add noise to that. And that paradigm was really gone after some pioneers of the field found really simple dynamical systems that showed complicated behavior. I see that there are 3 questions in the chat. So will there be slides used during the course, or are we expected to take notes? I do believe in taking notes. I mean, that's how I always learned, and I still, I find it for myself very important to take notes, but I realize that not everybody does that. You don't have to take notes if you trust my notes. So there's a master set of lecture notes, which is already up there. Well, it's like a clean set of notes, but it's handwritten. And I will be writing notes. Like I said, this PowerPoint is just for introduction. I have one more slide, and after that, I'll be writing notes. And after each lecture, I will upload those notes, and you can download them. So you will have 2 sets of notes, the master notes and the current online notes, which will be roughly the same, but I might be adding little things or leaving out, but mostly adding or insights. Okay, cool, thanks. All right. So this was the sort of the breakthrough model that that made people realize that simple systems can show very complex behavior. It goes back to meteorology professor at MIT, Ed Lorenz, 1963. He was very well respected around the institute. At the time when I was working there, well, it's now been a while ago, but early 2000s, he was still around, retired, but he still came in very regularly, and he was holding very high respect. What he was interested in was not at all chaotic dynamics or complicated dynamics, but he wanted to have a good reduced model for atmospheric convection. So he took the fundamental governing equations and did a 3-mode Fourier truncation. And after various assumptions, he came up with this model. And these are amplitudes of various interacting modes in his atmospheric convection model. And if you look at the system, it's largely linear, right? The first X, Y, Z are the 3 variables. It's a 3-dimensional system of differential equations. You look at the first equation, there's a parameter sigma there. So that's not a variable, it's a parameter. And Y and X are featured at linear power. So this is a linear equation. The second equation has some slight nonlinearity because rho is a parameter, but X multiplies Z. So that's probably the simplest nonlinearity you will ever have, a quadratic one. And the third equation also, beyond having a linear term minus beta Z, it also has an XY. So, from a engineering or scientific perspective, this is a very simple model, benign. And certainly at the time, nobody expected any complicated behavior from such a simple model, right? So Lorenz was running computer simulations on this, and he was really interested in the long-term behavior. And word has it that he, since he ran out of time on a given day and he wanted to continue the simulation, he was or didn't save it, or now I'm actually a bit uncertain about the details, but the point is that he wrote down the current solution coordinates at some point. And then he said, okay, I want to rerun that from that point, and maybe several times, but he ran it for different times. And then actually he got it to a certain point. Then he probed the variables at that point and wrote them down. But what he was getting is the variables up to just a few decimal high, but still finite number of decimal precision. And then he said, I would rerun the simulation from there, and clearly I should be getting the same result. So again, these were the amplitudes of the velocity modes. So again, I list here the time history of one variable out of these. This was the X variable. And I'm showing it. These are his original plots, I believe. I may be mistaken, but I forgot where I've taken this. This is not good referencing in my part, but it may well have been his original plots. So 2 very close initial conditions, which just means that he was jotting down the X and Y, Z values at a given point up to a good number of decimal digits, but perhaps not all, right? But he had every reason to believe that in such a simple system, the solution will be robust. So there are 2 initial conditions here that are indistinguishable to the naked eye, and then he would run them. And indeed, look how closely they're following each other. But at some point, they start differing. So now you see here 2 curves, and those 2 curves are, after a while, are completely unrelated, not even correlated with each other, right? And that he really found stunning, that with respect to just that small change in the initial condition, and that's virtually tiny. The 2 solutions are practically the same. He thought they were the same, but after a while, they started differing so dramatically. And he started looking into this, and this phenomenon has become known as sensitive dependence on initial conditions, and that had led to the whole terminology or field of chaotic dynamics. And that in turn gave a completely new boost to nonlinear dynamical systems, because people realized that, wait a second, there's a whole lot more to nonlinearity than we thought before. So this was the view. This is the Lorenz's. In fact, Lorenz's view on this phenomenon perhaps was even less geometric. He, as I understand and heard, that he went to conferences, and instead of plotting what you see here, he would have tables of numbers on his slides, and he was very excited to say that look at this here, look at this one, look at that one, and Kevin, and it was hard for him to get people excited about that because it wasn't so stunning, but that was his way of communicating his excitement. Now a bit more geometric is actually plotting these trajectories, probing one variable and showing two graphs and seeing, wait a second, these trends are different, but that's still not so much the contemporary way of showing it. I see myself frozen. Hi, everybody. Sorry, I don't know what happened. My computer froze completely. I dropped, so I need to reconnect everything. Apparently, we're still recording. I'll go back to the PowerPoint, finish that up, and then come to my tablet. So this is where I was. This slide. And then what I was saying at the time, is, I still don't see myself, but hopefully my PowerPoint, is it shared?
No.
No, not yet.
No, sorry. Okay, then I need to share the screen. Sorry. Okay. Can you see it now? Is it on?
Yes.
Yeah.
Good.
Right now.
All right. Thank you. Again, sorry about this. I don't know what happened. So let me share this. So this is already a step up, right? Because we're drawing a graph, but it's still not quite the contemporary view. The contemporary view is viewing what's happening in the phase space. And the phase space would be the space of the X, Y, Z variables. And again, one state of the system is the current value of the three Fourier amplitudes together. And that's going to be 1 point. And this is therefore a three-dimensional space in which the evolution of this whole system, the model of the atmosphere, the state of the atmosphere, is a trajectory. And this is a contemporary visualization of that. This is a single trajectory in the XYZ place producing this behavior. And the end result is this, what has become known as the Lorentz attractor. So what you see here is a convoluted surface. It's not a straight surface, but it's convoluted, it's folded over itself. It acts as what we call an attractor to the dynamics, meaning that if you start anywhere for this system, then ultimately these single trajectories will come to this attractor, will pick up its shape. But how do you explain then this very different behavior under slight variations in the initial conditions? The explanation for that is that the dynamics within this attractor is actually chaotic and sensitive. So different trajectories getting to it will not synchronize with something trivial such as a periodic motion, but they will be redistributed and mixed around this attractor. So that one of the trajectories that you see on the left, in fact, both of them, after some journey, they got very close to this attractor, but they also are drifting apart because within the attractor, there's complete chaotic mixing going apart. So they came very close, right? They were sticking together for a while, but then they are separating and doing completely different things. So that would be the modern view on this. So this would be just the type of illustration that I wanted to give you for what we mean by complicated dynamics, how it's very real. I mean, it is in the, certainly even the simplest model for the atmosphere has it. And what the current view on that would be in the phase space of a dynamical system. And we will be working towards establishing the tools that would enable you to have this type of an understanding of nonlinear systems. My last PowerPoint slide is the main objectives of this class. We're here to learn methods to analyze nonlinear dynamics without solving the underlying differential equations. So I think this is a major distinction between what we call nonlinear dynamical systems or dynamics and many other subjects, right? I was just chatting with a colleague, a more senior colleague, not long ago at one of the leading universities, and he said, well, there's no need actually for having a position in nonlinear dynamical systems or nonlinear dynamics, a professorship at that institution, because, hey, we all do nonlinear dynamics. And in some sense, he's right, because currently all the models that we are setting up in science, since computational power is readily available, they no longer have to be linear. We can do the computations. But doing nonlinear dynamics doesn't mean that you're solving numerically nonlinear systems of equations. The solver actually doesn't really care whether it's linear or nonlinear. Doing nonlinear dynamics means that you actually understand the nonlinear behaviors that are possible in your systems. You have tools to analyze them. You have ways to interpret numerical results. You have ways to anticipate possible behaviors. And this all requires hard knowledge. So just running a computer simulation or nonlinear system doesn't make you a nonlinear dynamicist. There's this famous saying, I don't know where it's coming from. If you said that a system is nonlinear, you have only said so far what it is not, which means you haven't really not said anything. You just established that it's nonlinear, right? If that's all you do numerically, you have not gone beyond saying that's this system is that is not something, right? To do actually nonlinear dynamics informally means you have the tools to analyze it, and you're not just running numerics and staring at the screen, but you really have more than that, a whole toolkit. So we will also develop intuitions for the geometry of nonlinear systems through numerical assignments. So some of the problem sets will be numerical solutions, but they will be informed by nonlinear dynamics, and you will need in nonlinear dynamics to interpret the results as well. And along the way, you will learn a few important techniques from applied math. So and I don't try to make this course overly mathematical, but when I see an opportunity to bring in mathematics that perhaps is new to you, or it also has uses in other areas, then I will do that. And finally, we will look at applications from various areas of engineering and applied science to the extent I can in this course. It's an introductory course, cannot be super complicated. So I tend to still pick interesting, simple examples for illustration. So that would be it. There was a question. So if the states of the Lorentz attractor were initially as far away from the attractor, would their distance stay constant until they reach the attractor, or would they divergence before? That's a good question. There may be other things in the phase space as well in a general nonlinear dynamical system that would force them to diverge. Generally speaking, back to this question, you don't need something outrageous to make initial conditions diverge from each other. In fact, linear systems can do that as well. All right. So if you have a linear saddle type dynamics, then two nearby initial conditions over time will separate. Or in fluid dynamics, you may just have as benign a flow as a shear flow. So any channel flow, just imagine fluid trajectory is traveling, that has a bit of shear in it. And that's still a very boring flow, right? It will still cause initial conditions, it will still cause initial conditions to separate from each other. So it turns out that this sensitive dependence on initial conditions by itself, as we will learn in this class, is not a hallmark of chaos, but it's one property of chaotic dynamics. So the answer in the context of the Lorentz equation, that if you're willing to force initial conditions to start arbitrarily close, very close, then they will stay arbitrarily close. That's what we will refer to as continuous dependence on initial conditions, right? But ultimately, once they get close to the attractor, they will separate. They have no choice because of the sensitivity, hyperbolicity, and mixing. These are all notions that we will learn about either part 1 of this course or part 2 of the course. Any other questions before I start with my notes?
Yes, Professor, am I audible?
Yeah, go ahead.
Thank you. So just a rather historic question. I hope you don't mind. I'm actually fascinated by how late chaotic systems were invented in this manner, because I mean, Euler and others have been solving the free body problem, or have been trying to solve the free body or m-body problem since the 18th century, right? And they were already encountering bits with the highly chaotic nature. And Poincaré, he was also around at the beginning of the 20th century, right? So does it have to do with the computational resources, or what was the reason for this relatively late introduction?
I think you're making good points. So these were mostly known, I would say, in the mathematics literature, that things can get complicated. A systematic discussion of what chaotic dynamics is, however, the properties of that were still missing. So people realized that mostly conservative systems, both Euler and Poincaré, were really looking at very high dimensional conservative systems, Hamiltonian systems, and in those they found the potential for complicated behavior. But their focus was still more about solving the systems, right? So they were stumbling on these complicated things more as inconveniences in their ultimate goal, which was somehow to get at least approximate solutions to the systems, right? Because what used the classical focus of dynamical systems or differential equations was to get explicit solutions to the extent possible. And then you can underline it twice and you're done, right? Lorentz did bring a different paradigm. First of all, he noticed this numerically. And the first time there was really a picture, there were numbers showing this in a physically relevant system, which was no longer conservative, right? And then people then realize that, okay, in real life and even in the simplest models, this can lead to really interesting observations. But in fact, because Lorentz was communicating this largely with tables of numbers, he had a hard time convincing the mathematics community that this is really something they should invest in. So in fact, he was going almost door to door, showing these results to various people. And it was then ultimately Jim York, who was at that time already at the University of Maryland, who really started looking at this more seriously, because by training, he was a topologist and was very interested in geometry. So he was not trained in chaos theory. And he coined the word chaos. That word didn't even exist before. And once you coin a good popular acronym for something, then that will draw people in, right? Recent example of that is machine learning, right? Machines are learning all of a sudden. So if you talk to anybody who worked with optimization algorithms before, and they would say, before that they were called neural networks and also fuzzy logic and things like that, and people didn't get all that excited about it, but somebody found the right name for it, for essentially the same technique. Everybody's talking about it because it's so, artificial intelligence, same thing, right? So a little bit of that happened with chaos per se as well. And then it sort of re-energized the whole field of dynamical systems and made it more geometric. Before that, it was all the study of power series and approximate solutions. So that's a good point. Thank you for that. Anybody else? Okay, so let's hope that we're not going to crash again. What I need to do is set up my tablet, which means I was already logged in with the tablet, but I have to log in again. Hopefully that doesn't bring additional complications. Excuse me for the delay. Meetings. No audio. And then what I want is share screen. Getting there. Start broadcast. I've logged in from another device. I stopped sharing here. Sorry for start share. Am I sharing? Yeah, okay. This I don't want. And I go here. So this is the type of file that will be saved under the link online lecture notes. Again, there's a different file. You can already find the full material there in a master set of lecture notes, but these will be resaved after each class and they will grow continually. Okay. And I have to watch my handwriting, but it's not easy on the tablet. But anyway, I make no excuses for my handwriting. If something is not clear, then please ask. I'll open up I try to open up the chat, and hopefully I notice it at some point when you have a question. Okay, so that's it. That's the header. And let's get started. So I just wanted to get some simple things out of the way at the beginning. And I try to follow the labeling that I have in the notes. So for the 0th chapter, if you will be the introduction. Okay. And within the introduction, I just wanted to have, not that I want to be overly pedantic or anything, but let's just actually discuss what a dynamical system is, because I don't think that's necessarily clear. So in applied mathematics, what do we mean by this whole area of dynamical systems, right? So a dynamical system, not at the most abstract level, but at somewhat abstract level, is a triplet, okay? So it's basically a space P in which you have some dynamical variable of interest, like the X, Y, Z variables of Lorentz, right? And then you have another variable space of variables, just a single type of variable, which is the evolutionary variable, which can be, as it turns out, either continuous, time just flowing continuously, or some discrete version of time. So that's going to be the space of the evolutionary variable. And finally, you also then have to, you're set up now, you have a, you are set up to go, so to speak, because you have a dynamic variable whose evolution you want to track. That's in P. In E, you define how you're going to track that. Are you going to be sampling the variable? Or are you going to be following continuously? So that's the matter of E. But the most important thing is still missing. How are you going to evolve? So the last bit is some sort of evolutionary rule, which this is script F. So to explain the notation that I'm developing here. So first P would be the phase space. For some dynamic variable. And that dynamic variable is some x, and it's taken from P. P, let's stick with P, can really be anything. It can be a set of discrete states. It can be a finite dimensional set. It can be a linear space. It can even be an infinite dimensional space. So you might actually not be evolving in a space for which you can write down, 3 or 4 coordinates or even 100. It can be an infinite dimensional space, a function space, which arises when your dynamical system actually is defined by a partial differential equation, as we might get to that at least briefly. The other space of relevance was E, and that's the space of the evolutionary variable. So basically a time-like variable. And let's just call it T, but it doesn't mean that it has to be your usual time. And that immediately brings a major partition of dynamical systems into 2 classes. I'll just write the abbreviation. In the notes, I write it out. Discrete dynamical systems. So DDS is discrete dynamical systems. And those are just simply dynamical systems where this evolutionary variable is hopping through some discrete values. So E will be, say, the set of integers, Z. Maybe you're not allowing all integers, because when I say integers, all integers, it means I'm also hopping backwards if needed. But maybe that's not possible in some cases because I only know the forward evolution. So I can just say T is taken, say, from the natural numbers, okay? In that case, when I only know the forward time behavior, sometimes that's called a semi-dynamical system, which means that I can't go in both directions, only in forward time. So what is a discrete dynamical system? Again, I'm sampling the state of the system at discrete points. So you might want to, think of some initial state x0. That's your dynamic variable, and then the next position will be x1, and then x2, and you're basically hopping from one state to the other, and in between, the state of the system is unknown. We then call the trajectory of the system to be the collection. The collection of these is just the trajectory of the system. So in this case, the trajectory would be, x0, x1, x2, and so on. What could you think of? I mean, for instance, you could think of a bouncing ball. This was actually a broadly studied system at some point in engineering. That you could have, you could have some sort of oscillating table here. This was really motivated by experiment in which people observed very irregular behavior. So this will be a ball which is bouncing on a vibrating table. So this vibrates, and it's a complicated system. So people were trying to look for simplifications, and this is very nicely treated in the Guggenheimer-Holmes reference that I gave you at the beginning. So they were trying to simplify this as opposed to following, this oscillation is imposed on the system, so you know exactly, but instead of following the whole trajectory of the system, they realized that it's enough to record the impacts. So it was not necessarily a stroboscopic sampling at the same time intervals, which you would often do, say, in fluid mechanics or in vibrations, that you stroboscopically sample states of the systems and you don't care about the in-between states. And this really brings out evolution sometimes a whole lot more than staring at all the states all the time. So it wasn't that. This was more about tying the observation time to a specific event, which was an actual impact of the ball. So you can say record the height of the ball, say h of t. But that by itself, as you can already guess, but of course, the way I'm showing it does not necessarily make much sense, but because I need to sample it, I want to sample it at the times of impact. So I should measure it here, from some fixed non-moving location, okay? And the two objects, the table and the ball, will hit each other at different locations at different times, right? So the idea was that whenever they meet, just record that. So I've just shown one instance here. So this would be then h of t n, or actually let's just call it hn, the nth impact. Now, would that define a dynamical system by itself? So that can I have any hope that if I record the position at which these two objects meet each other? So again, one of them is oscillating, the other one is bouncing on that, right? But it's not as simple as I'm showing it. They're not in sync. There's actually things can go pretty crazy in the system already. Is it enough for me to somehow hope that I will define evolution, or if I just record the positions? If we know mechanics, which we know some of it, then we conclude that it's most likely not enough, because if I only determine the position of the ball at the impact, from that, I cannot really deduce the next impact. Why? Because between impacts, it's just Newton's law that governs the motion of the ball, right? And Newton's law is a second order differential equation, as we'll get to that. So we know that not only do we need the initial position, but the initial velocity as well. So that's what people then ended up recording. So instantaneous position and instantaneous velocity, okay? And that those together can be, this is a definition, one point that you altogether want to record, and that would be your dynamical variable. So at each instance, you record where they hit each other, what was the instantaneous velocity of the ball at that point, say when it was leaving. And then you hope to form a discrete dynamical system out of that. And that would be your dynamic variable. That would be one example in which this view was particularly advantageous. The other one is the continuous dynamical system setting, which is the one that for which we've seen already an example. That would be, say, the Lorentz system or any other differential equation that you have seen. So in continuous dynamical systems, the evolutionary variable is no longer discrete, but it's, say, taken from R. So it's either running back, forward and backward time, or you could, again, you could have the concept of a semi-dynamical system, in which case you only move forward. You could say, all right, if I can move forward, why can't I move backwards? What stops me from that? The answer to that is that, amazingly, some evolution rules may be well defined in forward time, but not in backward time, okay? So some systems produce identical outcomes from different initial conditions. So we'll see examples of that soon. So that's why in those cases, you may have reason just to study evolution in one direction, because it's only well defined in one direction, but not in the other direction. In this case, the picture that we should have in mind is more of a continuous evolution, right? So then you start from some initial conditions here, x naught, and this is your current state, x of t, and you're just evolving continuously, right? So this is x t just evolves in this direction. In this case, the trajectory notion is different, but not fundamentally different. It's the same idea, that it's basically the collection of infinitely many points. So it's really a continuous curve in the phase space. So that's the two settings. Now, I've already then spent some time on this one, which is the phase space. Again, we'll see examples, but that's the variable you want to track here. This was the variable. And then the space of the evolutionary variable, of which the current position or the dynamic variable is a function. And finally, what's still missing, at least at the level of explaining this triplet, right, is the evolution rule. So I'll just write it out and then we'll get more into that. So finally, F would be the evolution rule. It basically just tells you how, defines the evolution of the dynamic variable from one state to next. And the next might be actually continuously varying, not necessarily in a discrete fashion. So what are the types of evolution rules that we can get? Because this is really the crux of the matter. So the types of evolution rules can be two different types, either one that's fitting the CDS, the DDS, the discrete setting, and ones that's fitting the CDS, the continuous setting. So the discrete dynamical system. So how can you define a discrete, or how are most often discrete dynamical systems defined? When can you consider one well-defined map? Well, you can consider one well-defined if somebody basically gives you an iterated mapping. That can also be implicitly given. So you some sort of relationship, implicit equation that defines the relationship of the current state to future states. But most often we desire it to be, we have results for systems that are really given in form of an iterated mapping or a recursion, which means that the current state of the system will be some function, in this case, generally speaking, nonlinear function of the previous state, xn, and also very often, although that's an inconvenience, of n itself. So that means that just by telling you where I am right now, I cannot uniquely say where I'm going to be afterwards, because I also need to specify the time, so to speak. So things change. Yeah. So for something is tied to, say, to some daily activity, then it does matter. For instance, if I want to describe the evolution of traffic per day, right? Then clearly I will have different types of traffic in the afternoon, in the rush hour, and so on. So if I try to describe how things will evolve, say in the short term, for at least for a few minutes, I do have to care about where I'm in time as well. So the evolution rule will change in time in the most general setting. However, we like evolution, the special case, which I mentioned separately, is when actually I don't have that dependence. So if the system is such that the evolution rule does not actually explicitly depend on n, so this derivative is 0, then we'll call this an autonomous mapping. So the term autonomous, or autonomous discrete dynamical system, I should say, in this sense, in this context, in dynamical systems, autonomous just refers to the fact that the evolution of the system is self-governed. There are no external factors, time-dependent factors that would influence it. So in that case, what happens is that xn plus 1, the next state, will be simply a function of xn. But then I can keep working backwards and realize that xn is just the application of x to xn minus 1, right? And if you continue working this out, then ultimately you have a composite application of n of f, n plus 1 times to the initial condition. And what we usually, the notation for this, we will say that I simply iterate the initial condition n plus 1 times to get from the initial condition to the current position, right? Note that not all dynamical systems are like this. And what you can, of course, do repeated application. You can always sort of evaluate this discrete mapping and get to the following state using this formula, but the general formula depends on n. So you can concatenate various applications of that mapping, but it will depend on n. And what I'm writing here doesn't depend on n. Therefore, you can write that it's basically the n plus first application of the same mapping rather than different mapping. And that has really important implications. And when the system is autonomous, then you can say a lot of things immediately without solving the problem. So let me give you the first example of this course. Also to illustrate the spirit of the course, that basically we would like to say qualitatively or even possible quantitatively what the ultimate behavior of the system will be. And it's a nonlinear system. And can we still say something without numerically solving the system, without necessarily numerically iterating a discrete dynamical system? Can we do that qualitatively so that our conclusions will be also robust with respect to changes in the parameters or changes in initial conditions? So let's consider a simple dynamical, one-dimensional dynamical system where the evolution rule f will simply be a mapping on the phase space, which is just an arbitrary interval. So it's one-dimensional, all right? And it will be just simply a subset of R1. So this is our mapping, f mapping from that space into AB itself, into P itself. This would be a one-dimensional mapping. And let's see, I need to be able to draw a good phase space for this one. So this is supposed to be a square. It never is, but it can be close to it. But I want it to be close to square as much as possible. So if you excuse me, I redraw it. So how should I redraw it? So I should start from here, I guess, so that I come back to the same point and then I can really have some control over the shape of this, right? So this is not close to a square, okay? Why is it close to a square? Why do I insist on that? Because it's gonna be a mapping that I wanna graph over A and B, a discrete mapping that tells me the next state of the system. And the range of that mapping also happens to be A and B. If it mapped out of A and B, it really wouldn't be a well-defined dynamical system, because the dynamical system, remember, the evolution rule acts on the same space, cannot take you out of that space. You have to then properly select A and B so that you stay in that space, but it has to, the evolution rule cannot lead you out of the space, because at that point, the dynamical system is no longer well-defined. So for one-dimensional discrete dynamical systems, there's a good way of understanding them globally without trying to really solve them and run them numerically. I want to illustrate that here by giving you an example in which I don't even know the exact details of the dynamical system. I only know the rough shape of the evolutionary rule, okay? So let's just assume that the rough shape of the graph of the system, and I just want to be, this would work for any system, but I want to be in line with the picture that I had in my notes. So it would be something like this. Okay, so that would be the rough shape of the dynamical system. So what you of the evolution rule. So what you see here, this is the graph of f, which I'm only specifying to this degree. For instance, it could be, for instance, maybe without detail, I can think of something which is f of x. And write that out in detail. Suppose this could be my discrete dynamical system, xm plus 1, okay, something that has this shape, just sort of roughly, very roughly. So this could be something like 2xn minus 3 squared plus 5. So it's an upside down parabola right? Because this looks like an upside down parabola, and its peak is shifted from this axis in the positive direction. So that takes care of that, right? That kind of shifts a parabola roughly to the +3 point. And I also shift it up like this, +5. But I mean, I just threw this out from the top of my head. It doesn't have to be that way. Okay, but I put this in parentheses because I'm not going to use that in any way. And yet now I have a discrete dynamical system defined. It's nonlinear. You would call this another subject recursion, and you would probably be encouraged to explore this numerically, or maybe use some tricks from analysis that you learned about series to figure out what's going on with this recursion. In the dynamical systems view of that, of the same side, you don't need to do that. So there's very simple tricks that you can use just based on the geometry of the phase space to figure out what the system is up to. So let's see how that works. I'm just going to draw a 45-degree line here, but I need a different color. I'll switch back to, oh, maybe I use this one. So this is a 45-degree line here, which will have a significance, and that's why this was important that I draw an exact square. So let me start here. Suppose I pick an initial condition here. So that's going to be my x0. And I'd like to understand what the fate of this initial condition will be under iterations of the dynamical system. So just by definition, the first, since xn plus 1, let me just write this as a reminder here, xn plus 1 is equal to fxn, and this is the graph of xn. What I need to do fundamentally is now evaluate this function f, whose graph is here, although I never gave you the function exactly. Just imagine evaluating this function, and it will return the next step in the dynamical system for me, right? So graphically, that evaluation just actually amounts to me doing the following, going up here, right, until I hit the graph of the function. And at that point, I can just really read off the outcome here. I need to change colors horizontally. And if that's all I care about, I could now really say that, hey, this is exactly what I was looking for. This is f of x0, right? And that would be end of the story. But that's not what I care about. I care about the long-term behavior of this system. So I'd like to then keep iterating the same value. So a neat way of doing that graphically would be the following, that instead of me exiting this process just here and reading of the outcome, why don't I just refeed this value into my little graphical iteration scheme? So one way of refeeding that value would be that I go now horizontally here until I hit the 45-degree line. And that's why I needed that 45-degree line. So I move in this direction. I still haven't changed anything there. But now if I come down here, I imagine coming down here. Sorry, I'm mixing the colors. So I imagine just coming down here vertically. This would still be, right, f of x0, because this was the 45-degree line. So I'm basically reflecting with respect to that. But I don't do that. I'm going to stop here when I hit the graph of this function. And the reason I have stopped here, because if I went down here and I fed this into the iteration again, then I would have to go up here anyway and do the same what I did in the first step, right? Because I need to go up to the graph until I hit it and read off the return value that I get from the function. So why don't I save some time, and instead of going down in my little graphical procedure and then going back up and evaluating it, just why don't I just immediately turn there? Like so. When I do that, remember what this is. This height here is just f of, I shouldn't keep varying the color, it's just f of f x0, right? Which is by definition, f of x0 was f x1. This was x1. And this is therefore f of x1, that's x2, right? So if I only cared about getting to x2, I would exit at this point, but I care about the long-term evolution, so I do the same thing, right? So I reflected it, I write it off here, and I just basically repeat the same procedure, that instead of exiting the process here and saying, okay, this is also x2, I'm done, I save myself that step and go up again, because my next step will be again to evaluate the function at x2. So I go up here. And I keep doing this. And this is supposed to be horizontal. See, if I keep doing this, then very quickly I spiral towards this point. And that point, which is the intersection of the graph with the 45-degree line, if I try to pick that as an initial condition, so if I pick its x value here, then you realize that I have nowhere to go, because this procedure would keep returning the same point there. So that's actually a fixed point, what we call a fixed point of this dynamical system, or equilibrium point. So let's mark that maybe with a different color. So I point there. So this is a fixed point of the dynamical system. And immediately I got a whole lot more information rather than just it being a fixed point. I also see how it relates to the other initial conditions or the other trajectories of the dynamical system. It's a stable fixed point, in fact, attracting fixed point, because actually no matter where I start, I will spiral into that, okay? So this is an attracting one. The first example of an attractor, the simplest example of an attractor is an attracting fixed point. We also call it an attractor. And the whole A of B, no matter where you start, just look at the whole geometry. If I experimented now with a different initial condition, very quickly I would run into the same game, right? So compare that view with some numerical solution of this, which you would only be able to do if I give you exactly what this function is, right? And I have never done that. And the power of dynamical systems is that we don't need that. And we can still, as long as you have some rough idea of your dynamical system, we can give you the asymptotics. We can also give you that, hey, things like robustness. People always ask, okay, so what uncertainty? I can tell you. I mean, if I just change this slightly, it's going to be the exact same story. Maybe that fixed point moves a little bit, but fundamentally the dynamics doesn't change, okay? You can also ask, oh, all the initial conditions go there and do that, or just some of them. I can answer that question too, because this construct is insensitive to the choice of initial conditions. So basically, just with a few steps, you get a global understanding of a nonlinear dynamical system without even knowing it explicitly. So that's kind of the power that we're seeking to get, the kind of knowledge that we try to get out of this course, rather than insisting on an explicit form like this numerically, or insisting on some knowledge, tricky reorganization of series that you might have seen for recursions before. And it's as simple as this. So basically everything you wanted to know about the asymptotic behavior, what the system is going to, is already there, okay? One thing that I wanted to point out is that a little bit back to the thing that I was raising here, whether I only want to iterate forward or backward, do I have any limitations? One would think that in a system like this, I certainly will have so simple, I will have no limitations. It's a smooth graph, right? It's well-defined, very simple. Why would I not be able to define a full-blown dynamical system, which I can also run in backward time? Now, you when you try that, you will see what goes wrong already in this system. Just look at this, do the following. Take this initial horizontal line that I was drawing, and now go in this direction until you hit the graph, okay? I'll use green for that. So I come here, and I come down again, and I still use the upward arrow, okay? I will call this initial condition x naught prime. And see what happens is that if you start, this is very different, the two initial conditions. And yet, if you start iterating this one, in one step, you end up doing the exact same thing as before. What does that mean? It means that your forward time evolution is still perfectly well defined. But if I took this point, say here, right, which was on this trajectory, and I then started to undo the iterations, then at this point, I would have two choices to go down, because now I have to go down after I have hit the graph, right? So I will have two pre-images to these points. So already there, I would have two different answers for the backward evolution of the system. Therefore, my backward evolution is not well defined. So in backward time, I don't have a dynamical system for that reason. The evolution rule is not invertible. Even though there's nothing funny going on. This is a perfectly nice example. So that basically x naught prime and x naught lead to the same evolution, to same trajectory. Obviously, they're two different initial points, but after that they join. So basically, no well-defined evolution in backward time, evolution rule. Only in forward time. Okay. So, any question? What if it crosses the 45-degree line twice? I'm not sure I get that. So, but the procedure is that the iteration procedure is this: that I go up here, right, and then I go horizontally to look for the 45-degree line, like that. Oh, the graph of the function. Okay, sorry, I didn't get that. If the graph of the function crosses the 45-degree line twice, such as this one, or it can even 3 times or 4 times, then each and every crossing is a fixed point. However, they're not necessarily stable. You can see some other situation. It really, we'll be going into that. It really depends on the slope of the graph here. It turns out that if the slope is less than 1 in absolute value, you get a stable fixed point. If the slope is larger than 1, you get an unstable one. And you can kind of play with that. Although I don't want to overcrowd this figure, but if I manage to, let's pick another color, which is different. What should I pick? Maybe this one. Whether or not that's different, I'm not sure. But I can imagine some other function which surely would cross this line several times, like that. So this would be the graph of, say, f tilde. And then that would have several fixed points, this one, and that one. And if you start playing with this game here, so I'm close to this fixed point. Say I start an initial condition here. What am I going to do? Well, when I hit the graph, I have to go horizontally. I go horizontally. Then what do I have to do? Then I have to go vertically until I hit the graph. All right, I go vertically until I hit the graph. Then I have to go horizontally until I hit the 45-degree. Okay, so you see what happens? Once again, I start incredibly close to this, and instead of getting sucked into it, I get repelled away from it, and I get sucked into the other one. So this one, the way I have drawn it, this was just ad hoc. This turns out to be stable, and this turns out to be unstable. So again, slightly more complicated function, immediately global conclusions. And again, I haven't done this, but now systematically, but the result will be that if the steepness of your function then is larger than 1 in norm, then you will be repelled. And if the steepness of the function is less than 1 in norm, like this one here, then you will be attracted. Okay, you can see here. I mean, sometimes it's not easy to see from my drawing whether this is larger than 1 or less than 1, but you could actually just try it out. So I go up here, what's my next move? I have to come here, right, to hit the 45 degree. Then I come down to hit this curve again, and then I have to go horizontally. See, okay, so it then had to be less than 1 in norm because I'm converging here. So in that case, this would be, this would be a stable fixed point, and this would be a stable fixed point as well. Okay, whereas this one would be in some other color. This one would be unstable. Okay, so this figure is a bit messy now, but it was a good question. So it gave me an opportunity to show you another example in which the function was not so simple. Very good question. Thank you again. 2 fixed points, then each unstable, probably nonlinear. Oh, so that was a response, because luckily there are people with the quicker cognition than I am here in the class, because I just said, wait a second, what's the question? But it was a very good question, and thanks for the answer. That was also very good. Okay. So that just for now about discrete dynamical systems and basically the power of qualitative thinking, okay? Because you do hear this opinion, oh, we have fast computers, you don't need to know the fundamentals. And by the way, everything is linear, right? Because actually that's sort of the promise of machine learning. But I also see that I'm running out of time, have run out of time. So I stop here for now. We'll continue tomorrow at 10. If you have questions, I'll stay on for a few minutes and I'm happy to take them. Thank you.
Maybe just a very quick one if
Sure.
it fits the time. I was wondering about the applications of maybe this is a bit personal. I was wondering about the applications of nonlinear systems in finance, or if you've stayed in the nonlinear world when going into the world of finance. Is it really applied there? I don't know the models or the frameworks that they use, and it's a mystery to me. If you can summarize in a few words and it fits the time, then it will be very interesting for me, but I understand if it's not the main course material. Yeah,
I mean, that's a good point. I happened to work on that for about 3 years for a Wall Street firm. And first of all, the dominant view in finance is that you basically, not just the view, but the reality, you don't have a good model. So what you have is very few fundamental principles too. I mean, in mechanics, we have, conservation of this, conservation of that, energy, variational principles. In finance, the only principle is virtually the no arbitrage, which is basically that you cannot make money out of nothing, right? Which unfortunately also doesn't hold because lots of examples show, non-liquid markets and so on. So basically, that's the only thing. There are beautiful, highly theoretical approaches that many of them lead to actually linear equations, but then basically the heart of the equation is not the deterministic part, or as they call the drift part, but it's the oscillations around them, because those oscillations will have a large impact on the price of the securities. In fact, that's the unpredictable part, which is basically brings the risk in versus the predictable part, right? That's what determines the prices of securities. And where there, it's anybody's guess. People use different models, which most of them are probably wrong in the long run. In the short run, they try to fit market prices if they can. Then it was okay for a while. They throw in Brownian motions or Poisson processes. So it's always been sort of a big mystery to me. But there are incredible successful theoretical results in finance. If you accept the models or the postulates there, I always felt that the big challenge in finance was the disconnect between these absolutely beautiful theoretical pieces of fantastic achievements, some of them Nobel Prize winning achievements, versus the actual market, for which the data is often unavailable or not detailed enough or unreliable. The probability measures used in finance are not the historical probabilities. If you look at a distribution of something in the past, that's not what goes into the equations. What goes into the equations is the distribution of expectations. So what do people expect to be the distribution of outcomes in the future, right? So that's called the pricing measure, pricing probability measure, which is not the same as the historical measure. So there's a lot of room there for improvisation and modeling. And the last big credit crunch in 2000, when was that, 9, a while ago? 8, 9, the outcome, right? Yeah. I personally had to survive in the world of finance. Yeah. It was a good example of that people had no idea at some point. But as long as the cash flow is coming in, all these models were accepted. I'm sure, I'm out of that area. I'm sure there's been a tremendous improvement since then. I haven't followed it, but there's a lot of engineering going. It's called actually financial engineering these days. But these deterministic models would not be applicable there because of the tremendous uncertainty and lack of information.
Right, thanks for the insight.
No problem. Anybody else? Okay, so why don't we call it quits for today? Thanks for your attention. I'll see you tomorrow, and sorry about the technical difficulty. Hopefully we won't have any of that tomorrow. Take care. Bye-bye.